Welcome to the uh, first workshop on generative AI for smart and connected health. My name is Yuan Xiongguo. I'm from UT San Antonio. So today, we for this workshop, as you may have received several emails from me, so we have kind of a diverse, large group of organizing members. So the first, I'm Yuan Xiongguo, and as I mentioned, and we also have Xu Wang. He's there. Okay, from Florida International University. We also have Fen Liu, and I think he just left. Okay, from Stevens. Also, we have Yan Gong from the UT San Antonio, and Li Xin Song from the UT Health San Antonio. And finally, you have Dr. Lan Kong from Purdue University. And interesting thing about our organizing committee is that we have 6 persons, 6 researchers, but they are from totally different departments. Okay, so, before we start, I will say that here's an overview of our program today. This afternoon, we will have 1 keynote speech, and we have 5 long oral presentation and 9 short oral presentations. So for the 5 long oral presentations, we will have for each of the presentation we'll have 10 minutes, and we have some question and answer minutes until the end. Also for each short presentations, each of the presentations is 5 minutes. Okay, so we have session chair to coordinate that. So. Also, since we are talking about large language model or generative AI, right? So we know that how powerful it is. So that's why I kind of gave the ChatGPT list of our paper titles and asked the ChatGPT to generate those kind of categorize them into different groups. And we found that they have done ChatGPT has done a great job. So it divides our papers into 5 different categories. So the first category is the generative models for medical imaging and data augmentation. So basically, you are trying to use generative models to generate some synthetic data for model training. So the second, so we have in this category, we have 5 papers in total. And the second category is that how to ensure the privacy, security, or general trustworthiness in generative AI systems. So we have 3 papers in total. So the third category is the language models and question answering in healthcare. So we have developed some specialized or customized chatbot to address the medical problems. The fourth category is called AI for clinical decision support and health monitoring. So basically, we are trying to develop new AI models to address those kind of medical health problems. So the last one is that we're going to use the generative AI for not just the traditional healthcare problem, but also the bioinformatics and genomics problem. We have 1 paper there. So those are the handout. So we'll give you a sense about what will be discussed in today's workshop. So, after that, so I'm going to introduce. So first we have a keynote speech. So the original keynote speaker, Dr. Chunhua Wen, cannot be here due to some unexpected matter. So we have Dr. Zhang from Dr. Wen's group. So he will do a presentation today on behalf of this Dr. Wen's group. Okay, so let me first introduce Dr. Zhang. So Dr. Gongbo Zhang is a postdoc researcher at Columbia University working under the mentorship of biomedical informatics expert Dr. Chunhua Wang. So with a strong foundation in computer science and deep interest in natural language processing, so his research centers on biomedical text mining, particularly leveraging the generative AI and the large language models to extract and summarize clinical evidence from PubMed. And Dr. Zhang earned his PhD in computer science from the University of Delaware, where he specialized in text mining and machine learning. So prior to academy, he brought his technical expertise to industry as a software engineering at Google Cloud, so contributing to scalable AI solutions. So his recent projects push the boundaries of clinical NLP, natural language processing, aiming to bridge the gap between raw biomedical data and actionable insights for healthcare professionals. So his recent contribution to the literature includes methods for bridging the gap between open source and closed source large language models, and for addressing the challenges facing the use of long text to support retrieval augmented generation. So let's welcome Dr. Zhang.
Thank you, Dr. Guo. Thank you for the wonderful introduction. And thanks, everybody. Today, we are going to talk about the role of generative AI in modern evidence-based medicine. So my name is Gong Bo. I'm a postdoc at Columbia University Irving Medical Center, and my great pleasure to be here to present this keynote topic on behalf of my mentor, Dr. Chunhua Wang. I started working with her on this topic since 2023, and I want to share one fun fact about myself. As you can tell, I'm now native in English, so when I speak English for over 5 minutes, I begin to stutter. So if you want to be interactive, if you have any question, raise your hand. You are doing me a favor. You are not interfering. Okay, so let's start then. So let's start with what is clinical evidence. Clinical evidence refers to data and information that is gathered from research studies to determine the safety, efficacy, effectiveness of medical interventions. In the medical community, the use of evidence-based practice, evidence guidelines is so emphasized to improve the healthcare outcomes so that all the medical decisions are informed by the best available medical research. So the major challenge in adopting the best available evidence stems from the sheer volume of information. Here I want to share some quick facts. Since 2020, within 5 years, over 100,000 clinical trials have been registered. And a recent study pointed out that the average time that is required to publish a systematic review would be about 70 weeks. So random clinical trials are usually considered as a high-quality source of evidential information. While they are rigorous design, their practical applicability is sometimes limited because of ethical dilemma. For example, you cannot really administer potentially harmful interventions on patients, and sometimes due to a cost constraint or other factors. For example, for rare disease, you really cannot recruit enough patients to conduct a study. So for these reasons, there has also been a move towards the application of real-world data, which has an even larger volume than RCT. So why AI is relevant? Before we touch on that topic, let's look at what evidence looks like. So evidence is typically documented and distributed in text formats. And like in many other domains, we find ourselves overwhelmed by text data. For example, doctors need to keep up with the latest knowledge of disease and treatments, and which is disseminated in scientific publications. Electronic health records, they have been widely adopted as a central data hub for disease history, lab results, imaging data, and treatment plans. And the EHRs are produced at a very fast speed. Other data sources include health insurance claims, education materials, and this long list goes on and on. So due to the rapid growth of biomedical literature and clinical data, traditional approaches for evidence management are struggling to keep up. So there is an urgent need for modern approaches for medical evidence management that should be scalable, that should be trustworthy. So recently, we see dramatic advances in generative AI. In particular, large language models demonstrated a remarkable capability in handling natural language for assisting the process of collecting, extracting, appraising, and synthesizing the evidential data. So with modern AI technologies, we envision a more efficient and productive future of extracting and summarizing clinical evidence. So we are going to talk about 3 topics we have touched on. We are going to talk about concept extraction, clinical evidence summarization, and question answering. We will discuss about the challenges we encountered when we actually deploy language models for these tasks and present our approach to overcome these challenges. So the first work we will discuss focuses on extracting PICO elements from our randomized control trials, or RCT for short. PICO is widely adopted framework that is used to define clinical questions. It defines participants, intervention, comparison, and outcomes. And an automated extraction system would significantly reduce the manual effort in analyzing large volumes of trials, which will also facilitate aggregating multiple trials in downstream. So the task of PICO extraction is to identify those text spans within RCT records that denote PICO concepts. Here we're showing an example on the slide. So this task has been approached as a named entity recognition following a BIO tagging scheme where B denotes the beginning of an entity, I denotes the inside of an entity, and O denotes the outside of an entity. And there are multiple modeling techniques have been proposed, sequential modeling, including hidden marker models, conditional random fields, recurrent neural networks, and recent foundation models also demonstrate competitive performance. But the sequence labeling problem, the models, they have limitation. They are not designed to handle this overlapping structures of entities. In this slide, we see that an intervention entity is embedded within a participant span, and a traditional sequence labeling problem cannot handle this task. So to combat this issue, we propose a span-based method where we first propose the boundaries of entities and then enumerate all possible span candidates and then classify the span candidates by the PICO categories instead of labeling the BIO tags directly. By doing this, we can capture overlapping entities. So the first work, we benchmark our approach on multiple data sets, both with overlapping entities and without overlapping entities. EBM-NLP, that's the first data set, large-scale data set with PICO elements annotation. PICO corpus is derived from a corpus specifically focusing on breast cancer. And our collaborators from Yale also curated two data sets of clinical trials focusing on Alzheimer's disease and COVID-19. So here our system, PICO-X is the codename of our system. It demonstrated a significant advantage by a large margin as compared to those baseline systems. Our model is built on top of a BERT architecture, and we compare our methods against several widely adopted BERT models that have been specifically prepared on biomedical literature. So quick summary. We've developed this system that can identify overlapping entities, and I want to emphasize that the concepts that can be extracted are not limited to PICO concepts. And there are also other challenges in this PICO concept extraction that I cannot cover today. For example, this PICO structure is not a flat structure. It has a hierarchy. For example, under participants, we have demographics attributes, including age, gender, race, and the subcategories under outcomes is even more convoluted. And in order to capture those fine-grained attributes, that will require a tremendous amount of annotations. And recently, we published a work in JAMIA about how to leverage limited amount of data annotation and as well as large amount of unlabeled data to achieve competitive performance. I compiled a list of references at the end of the speech. Okay, so let's move on. So concept extraction, we just talked about, is relatively straightforward to evaluate. So as long as we can tell whether the model can correctly identify the boundary of the spans, as long as we can tell whether the model can correctly categorize the spans by the PICO categories, we can tell how well the performance performed. But for some tasks, even the evaluation could pose a significant challenge. Text summarization is such a task. This is because there is no single correct answer for text summarization. Next, we're going to talk about two studies on clinical evidence summarization. So a little bit background about this study. This study was conducted by our group before I joined Columbia. It was conducted in late 2022. Back then, GPT-3 was just released, and ChatGPT was the most popular application downloaded globally. It accumulates millions of users within an extremely short period of time. And this is unclear what this means to the biomedical NLP community. So in this study, we evaluated GPT models on summarizing medical literature. We select Cochrane review abstracts, which follow a well-defined format, providing detailed background, methods, results, and conclusion. By the way, The abstracts of systematic reviews, they differ from the regular paper abstracts. They follow a well-defined structure, and each of them can be treated as a very detailed abstract. Oh no, a very detailed article. So we choose the author's conclusion section, the last section of the abstract, as the human reference. That's the golden reference we are going to use. And the section contains the most salient information of the studies. And the other sections are used as input. We designed two experimental setups. In the first setup, we provided the entire abstract, the entire article, except for the conclusion section. And in the second setup, the models are provided with objectives and main results. So our data is collected from 6 distinct clinical domains: Alzheimer's disease, kidney disease, esophageal cancer, nephrological conditions, skin disorders, and the heart. The domain experts verified each review to confirm that all the selected data samples have significant research objectives. The right 3 columns show the number of words and the number of abstracts, the statistics of the data set. So this is the prompt that we use. We instruct GPT to summarize the article in 4 sentences. We select this number because this is closest to the average length of human summaries. We adopted several approaches to evaluate the summary quality. We first employed various automatic metrics, including rouge, media, and blue. And basically, they measure the overlap between the golden reference and the machine-generated content. Their value ranges between 0 and 1, and a relatively high score indicates that a perfect score would suggest that the summaries recover most of the salient information from the input, while a low score implies that the golden reference is written very differently from the machine-generated contents. And our findings reveal that these models exhibit similar performance with respect to these automatic metrics. We also assess the degree of abstraction and extraction. So extraction measures the percentage of words that models would take the words from the source input directly. And we also measure abstractiveness. That is measured as the percentage of novel words in the summary. And compared to human summaries, we found that large language models tend to be more extractive than abstractive. And this agrees with the way how summarization systems are prepared. If you look at how summarization models are pre-trained, they used a methodology called gap sentence generation, very similar to the idea of a masked language model. They take out one sentence and try to train a model to recover that sentence. That's why these language models demonstrated more extractiveness than abstractiveness. And to obtain a more comprehensive understanding of this summarization capability, we also conducted a human evaluation of the summary. Our evaluation defined the summary quality along 4 dimensions: coherence, factual consistency, comprehensiveness, and harmfulness. And first, let's look at coherence. This refers to the quality of a summary being clear, logical, and well-organized. So annotators rated that most of the summaries, they are easy to read. They are very coherent. I want to take a pause here because we know that modern language models are built on top of transformer, which is designed for machine translation. If you think about the machine translation software 20, 30 years ago, the quality of machine-generated content is very low. So this attributes to the recent progress in language models. Another thing is the factual consistency. It measures whether the statements in a generated summary can be supported by the input document. And our evaluator estimated that about 10% of summaries produced by ChatGPT exhibit factual error, inconsistency errors. The errors include fabricated information, contradiction with the input, as well as misinterpretation results or certainty illusion, where the authors believe that there should be no enough evidence to support the use or refute the use of an intervention, but the GPT says it with very high confidence about the medical intervention. It's worth pointing out that medical evidence summary should be strictly accurate. there should be zero tolerance for factual inconsistency. Next is the comprehensiveness. That measures whether a summary contains all aspects of key information from the input articles. And we see that GPT models, they provide very comprehensive summaries in more than 75 of the cases. I think the ChatGPT using the main results demonstrated the most comprehensiveness as compared to other configurations. The next evaluation, this is very interesting. It was conducted to determine harmfulness. So whether the omission of some key information might lead to medical harm. I think this is related to factual consistency. The harmfulness refers to the potential of a summary to cause physical or psychological harm or undesired changes in therapy because of the misinterpretation of information. And our domain experts believe that less than 10% of summaries, they could be potentially harmful. So in the first study, we systematically examined the capability and the limitations of language models in performing zero-shot medical evidence summarization across 6 clinical domains. And we conducted both automatic and human evaluation, covering several dimensions of summary quality. And we found that automatic metrics like blue, rouge, those are very widely used in machine translation and text summarization. They usually do not strongly correlate with the quality of summaries. That being said, in order to reliably evaluate the summary quality, we still need to work closely with human experts. So in that previous work, we just talked about the evaluation of GPT models. That's one of the most capable model families that we have seen on this planet. But the disadvantage of GPT models as a closed source software is rarely discussed or mentioned. I'm very sensitive to this. Imagine that you are going to build an intelligent system on the top of a GPT using their API. Then imagine one day that 50% of the nodes in OpenAI cluster crashed. Your service on top of that have to come at a stop, and you have little control of that. And the limitation of closed source software also include other dimensions. I will give an example. GPT 3.5 Turbo is very widely used in informatics domain. Many research groups benchmark GPT 3.5. But GPT 3.5 has been released with multiple model checkpoints along different periods. And I found that some of the checkpoints, when they become deprecated, they are not searchable anymore. That means when you use a new checkpoint, you have a difficulty reproducing the results reported in early studies. And again, since you are using closed source models, there is very limited things that you can do to control this. So open source models, they provide a promising solution to mitigate the above risks. Several open source model architectures were proposed to specifically summarize documents or for general purpose or as general purpose foundation models. Well, they mitigate most of the risks. There's a trade-off. The status quo of language model is that open source models, they usually fall short on benchmark performance. They are not as useful and usable as closed source models. So it is unclear to what degree some existing optimization strategies can help bridge this performance gap. So in this study, we experimented with 3 broadly used open source models, Primera, Longity5, and Llama 2. Primera is developed by Allen Institute of AI, AI2 for short. It deployed a pre-training strategy called named entity pyramid to select and aggregate salient information. Longity5 comes from Google. It is an extension of T5 architecture and adopts a summarization pre-training strategy to scale up with the input length. And when I conducted the study, Llama 2 was the only open source model. It was released, this paper was submitted before Mixtro was published. So we all know fine-tuning. Fine-tuning is a method of improving pre-trained models, training it on a relatively smaller data set for a particular task or domain. So fine-tuning itself can still be resource-intensive, requiring significant computation power and memory. If you fine-tune it on AWS, it will cost money. And there is another limitation about fine-tuning that is known as catastrophic forgetting. That is, after you tweak the model parameters of an open source models, the model used to be good at some tasks, but since you tweak it, it cannot perform that well. I will give you a concrete example. So starting from Llama 3 or Llama 2, the models have the capability to follow instructions and output the response in JSON format. But if you fine-tune that capability of following instruction will be lost. So to combat the above issues, we employ a pivot method, low-rank adaptation. So the high-level idea is that instead of updating all the model parameters, it keeps most of the parameters frozen and introduce trainable low-rank matrices, which can be viewed as actual parameter and can be reconstructed model weight matrices. Here's the data. We collected a more comprehensive data set as compared to the previous one. We collected 8,000 abstracts of systematic reviews from Cochrane Library, and now the collected reviews cover a wide range of topics, including neurology, gastroenterology, rheumatology, nephrology, and radiology. The publication dates of the reviews range from 1996 to 2023. And all large language models, and the training and the test split was divided by timestamp. All the models were prepared with a large collection of text data, and this data is collected until a certain moment known as the cutoff moment. So to maintain a fair comparison among these models, we use all the articles published after that time point as test data, and all the articles published prior to that timestamp are used for training and validation only. And in the evaluation, following the previous practice, we first used the NLG metrics. They are not, including Rouge L, Media, and the CHRF. They are not perfect, but they are indicators of generated summaries. An extremely low score will indicate a very poor quality of the generated summaries. In this figure, I show the baseline performance before fine-tuning in red, and the performance of fine-tuned models shown in sapphire, and we observe that after fine-tuning, the quality of generated summaries was significantly improved. I will show an example and see why they improved. Another observation is that Llama 2 and Primera, they demonstrated a relatively smaller degree of improvement. Primera was improved from, you can read the numbers on this page. Compared to Long T5, the degree of improvement varies by model architecture. That means even we use the same strategy, we use the same training data, the performance boost will vary. So let's look at some concrete examples and understand why fine-tuning would help. Here we show an example conclusion from a systematic review, and the summary is generated by fine-tuned Long T5 model. And here I highlight the key information, the PICO concept that I mentioned. First of all, the sentiment remains consistent. The above shows the reference summary, below shows the machine-generated summary. The sentiment is that this review found not enough evidence to either support or refute the use of medication, and that medication intervention is either single-room isolation or cohorting. The population is neonates, which is semantically equivalent to newborn infants. So with that being said, I think fine-tuned models did a fairly good job at capturing this key information. So we also manually compare the summaries generated by zero-shot models and the fine-tuned models. We found that zero-shot models tend to present a very detailed background of the summary study, but they do not provide any findings or conclusions. They present a very high resemblance of the leading sentence of the paragraph. And the verbatim generation is, well, we just talk about how the summarization system was pre-trained. We take out one sentence and try to train the model to fill it back. And when we train the language model for text summarization, it's our human writing habit that we usually deliver the key information in the leading sentences. So when developed summarization system, we usually take out the leading sentences And that's why the zero-shot language model tend to replicate the leading sentence of the input. Well, as compared to the zero-shot models, fine-tuned models they align more closely with ground truth summaries, and they provide supportive evidence or identify the lack of sufficient evidence for the intervention and outcomes. The next thing we observe is that sometimes fine-tuned smaller models would outperform zero-shot larger models. We fine-tuned the LangT5 base model, which is based on the same architecture but has only 10% of the model as the LangT5 extra large. The performance of extra large is shown in red, and performance of the base variant is shown in sapphire. And we see that the fine-tuned base LangT5 model, they outperform the zero-shot larger variant. So this observation also holds true across different large language model architectures. In our study, primary and LangT5, they have significantly smaller number of parameters as compared to Llama 2 70 billion. But still, after fine-tuning, the fine-tuned models outperforms Llama 2. So this may not be a new idea, but given the context when this study was conducted, people used to believe in scaling law, meaning that the larger the model, the more powerful, until people figure out that in order to serve the model, we will use a technique called knowledge distillation, basically use like a powerful model as a teacher, spill out some knowledge, and then train a smaller model architecture to replicate those model behavior. But in this study, we observed that even with some smaller models, if you only need to perform very well on a specific task, you really do not need to have a very, very large model. Let's just think about a transformer architecture. I think transformer is designed for machine translation, which is a very complicated task. It needs to go back and forth between two languages. Yet, if you look at transformer architecture, it only consists about like 30 layers of encoder or decoder. It's fairly small compared to even BERT models. I think while people are chasing after large language models, we believe that if we only want a task-oriented model, it doesn't have to be very large. So we also conducted a review of the summary quality via human evaluation. So before we dive into that, let's look at a comparison between the fine-tuned LangT5 with GPT 3.5 Turbo. That was the best model back then. And we see that they all capture the key information, the single room isolation or cohorting, and they also find the same sentiment. They cannot find enough evidence. And GPT 3.5, I think because of this post-training called RLHF, reinforcement learning from human feedback, they are prepared to be helpful, honest, and they are very verbose. They present very detailed information. While fine-tuned models, they align more with the human reference, which are very succinct, only consisting of a few sentences. So we also conducted a human evaluation. We define the quality along several dimensions. The aspects of the high-quality summaries include consistency, comprehensiveness, specificity, and readability. And we invite 7 clinical experts, and each of them received 35 pairs of summary, one generated by zero-shot Llama 2, and the other is generated by a fine-tuned models. And we see how much performance gain we will obtain after fine-tuning these models. So in this slide, we show the performance of the zero-shot Llama 2, fine-tuned Llama 2, and the fine-tuned LangT5. The default baseline performance is set as 50%, given that Llama 2 is compared to itself, and all the ties are broken randomly. So the baseline rate is going to be 50%. And we see that all the fine-tuned models, they outperform the baseline. And this figure shows that the human this figure shows that smaller models, Primera and Lanti 5, they are much smaller than Llama 2, but after fine-tuning, their performance could outperform those larger models. And these slides show that fine-tuned models, where they perform well, they tend to produce more comprehensive, consistent, concise summaries than the baseline. Lastly, we conducted a GPT-4 simulated evaluation. So just like the labeling task, it's a very tremendous task to manually prepare the annotations as well as evaluation. Like the reported in the first study, in order to reliably evaluate the summary quality, we need to involve human experts. And we try to understand whether a model could perform the task. And according to our analysis, the agreement between GPT-4 and human experts are about 70%. And according to GPT-4 simulated evaluation, language models produce better summaries after fine-tuning. And this agree with our observation with the human evaluation. And according to this simulated evaluation, Lanti 5 demonstrated the best performance, followed by Llama 2, Primera. And this observation is consistent with human evaluation. In addition, we believe that after preparing the language model, it's just a matter of how we want to prepare these models. If we include more and more tasks in the pre-training, we believe that language models in the future will have a chance to perform competitively as human evaluators. So let's do a quick summary. So we talked about the limitation of using closed source models as dependencies. And from the experiments on the models of various architectures, we demonstrate that fine-tuning is a robust technique for model optimization. And we conducted both automatic and manual evaluation. And we found that fine-tuned models would achieve similar performance as the best model, as GPT family. So remember that while we are selecting those models for document summarization, there's a slide that I show that we have to select models with a large enough context window. So originally, the first generation of foundation model, BERT model, they can take up to 500 tokens. They are designed to handle a pair of sentences. But if your input only consists of 2 sentences, there is really not much to summarize. So recently, when you see the newer models, we found that we see an increase in their context window. They can take more and more input tokens. With this increment in the context window, we can do more things than before. But we are also seeing some new challenges. Next, we are going to talk about question answering with retrieval augmented language models or retrieval augmented generation. So the limitation of large language models, it has been discussed in multiple places, including dependency. It depends on the extensive training data, and it is criticized for knowledge cutoff, meaning that it is capable of pattern matching against the pre-training data, but it is not capable of handling new findings, which is not ideal in scientific field, because we keep publishing paper, we keep finding new things. And it is also criticized for a lack of in-depth knowledge. But if language models can be paired up with an external knowledge base, and the models can leverage their external knowledge sources, then these limitations could be handled. This is the general idea of retrieval augmented generation or retrieval augmented language model. It's a pivotal evolution. But there's a problem. So general retrieval augmented generation consists of 2 modules. One is the retrieval system, which allows the user to search across an external knowledge database. And then the retrieval model, just like Google or any other search engine you see, you input a query and then you see a list of returned items. But there is no guarantee that the information that you are interested in will always be ranked at a top position. And what would happen if the position is ranked in the middle of the retrieval result somewhere? This is totally happen. This can possibly happen because you never expect a retrieval system to be perfect. If this happens, then there will be an issue called lost in the middle. So this study comes from a Stanford group published in TACL. They report that when the key information is not located in some spotlight position, then the information will be lost, will be ignored, will not be utilized effectively by large language models. So using retrieval augmented generation is a nice idea, but still, if it depends on an upstream retrieval system that is not perfect, then we still cannot fully release the power. So while we are investigating these strategies, there are some existing strategies. For example, what about we fine-tune the model to locate the key information? I see people do that. And the problem with that is we already discussed, if we fine-tune the model, there is this catastrophic forgetting. The model used to be good at something, and after you fine-tune it, it's just good at one thing and become very bad at the others. And some people just manually adjust the attention weights. The same thing would apply. If you take model parameters not in a systematic way, there will be consequences. And another thing is that even for fine-tuning, it still requires tremendous annotations. So I'm wondering if we can address this problem without changing the model weights, and we can still handle this lost in the middle issue. So that's known as, so I named this system called brief context. I borrowed the idea of MapReduce. So MapReduce was a framework introduced to handle large chunk of input. If you think about you want to sum up 1 billion numbers, if you write a for loop, it will take a very, very long time. What if you can break this 1 billion numbers into 1,000 patches and dispatch these 1,000 patches into 1,000 nodes and let the nodes do the processing in parallel? That's the general idea of MapReduce or Hadoop. So I borrowed that idea in MapReduce in the hope of that when we break a very long context into smaller snippets, each snippet will receive enough attention. We will ensure that every snippet of information is put on a spotlight in a smaller batches, and then we aggregate the results. So this is the research questions in this study. Can we reduce dependency on retrieval order without changing model weights? Can large language models resolve the conflicts in the contextual information? Do large language models favor short context over long context? And last, can the occurrence of loss in the middle be predicted? So this is the data set that we are using. We benchmark our data set on a wider variety of medical QA data sets. And in addition to this data set, we also curate a collection of open-ended questions. So most of the open source benchmark data set, they are in the format of multiple choice. This is a simplified form of question answering because you are offering options to these models. But imagine when doctors, they are taking care of patients, they do not have options. What about open-ended questions? So that's why we also curate a subset of 48 questions. We call that MedQ48. And this is the external knowledge database, knowledge sources. We follow a previous practice. We use the PubMed abstract, which is publicly available, maintained by National Institute of Health. And we also use the MedQA. That is a collection of education materials very widely used by medical students to prepare for exams. So let's look at the first research question. Can we reduce the dependency on retrieval order without changing model weights? To answer this question, we perform both control experiments and the integrating task. In the control experiments, we control the position where the key information is located. We will manually locate the key information at the beginning of the batch, in the middle of the batch, or at the end of the batch. And in the integration testing, we just use a retrieval system. We use MedCPT, specifically developed for retrieving articles from PubMed, developed by our collaborators from NLM. And we use BM25. BM25 is a general purpose language model built on top of an inverted index. So on this figure, we see that the first column shows the the top position of the context window, the 100th percentile represent the end of the retrieval context. And when the key information is located in the middle, that is the 50th percentile. The regular RAG usually perform very bad. But by breaking this long context information into smaller batches, we demonstrate that our system would utilize the external information more effectively. So this is the integration testing. We compared our BC is short for brief context. We compare our system against RAG, the regular RAG paradigm. We compare our system to chain of thought prompting. And our performance demonstrated statistically significant improvements. Now the question is, can large language models resolve the conflicts in the contextual information? So sometimes when you retrieve articles from the external knowledge sources, they do not support or refute this conclusion in the same direction. That being said, sometimes they include conflict information, and they are not equally trustworthy because of the quality of the studies. For example, some of the clinical trials, they are conducted more rigorously, follow the design protocol, while the other clinical trials, they can only recruit a small sample of participants and resulting in biased results. What if the retrieval information contains conflicts? Can large language model resolve that? And here, we see that if we break the context information into batches and the distilled information from each batch conflict each other, will language model resolve that conflicts? And the answer is yes. We highlighted the win rate and lose rate in different colors, where win means brief context can answer a question correctly, but the vanilla RAG paradigm cannot. And similarly, we define the lose rate where we answer the question incorrectly, but the RAG answer the question correctly. And we show that by breaking the long context into shorter context, our performance gets better. The overall performance gets better. The next research question is, do large language models favor short context over long context? Let me elaborate on this a little bit more. So I have a constraint, that is, I ensure that the key information, that is, the article contains the correct answer, is always included in the external knowledge source. But I control the length of the external knowledge source. Will shorter context result in better performance than long context? And the answer is yes. We experiment with several top K, where top K means number of articles we retrieve, and the key documents is always included in the retrieval results. And we show that when we guarantee that the key information is there, the language model always they always have an easier time to pinpoint those key information. And here I also want to show some upper bound and lower bound. The lower bound is just vanilla chain of thought prompting. We provide no external knowledge to the language model. Well, the upper bound is going to be the oracle setting, where we only provide the key information. We do not mix the external knowledge with any noise. And we show that, yeah, the shorter the context, the better the performance. But we need to guarantee that the key information is included in the context again. So this means that RAG's performance is not guaranteed to always improve your large language model limitations. You also, the degree of improvement also depends on the upstream retrieval system. So lastly, the question is, can we predict the occurrence of loss in the middle? Why do we want to predict this occurrence? The reason being that, imagine we are breaking the long context into multiple smaller contexts. We are issuing more requests than one single request in the RAG. That will incur some extra cost. And in the spirit of cost effective, we want to predict whether the loss in the middle indeed occurs or not. If this issue do not occur at all, then there is no need to launch a brief context or map-reduced workflow. So we very briefly adopted a rule-based prediction. We just check the overlap or agreement between two different retrieval systems based on very different retrieval architecture. One is based on dense retrieval called MetCPT, where the query and documents are represented in a very condensed vector representation space. The other uses BM25, which is built on top of inverted index. That's the traditional information retrieval system. And we use the IOU between these two retrieval results as agreement, and we show that the precision recall on F1 of this prediction is 50% precision, 90% of recall, and 65% of the F1. So this is tunable. If we change the threshold, we can do the trade-off between precision and recall. But here I favor high recall, lower precision, but this is changeable. So let's do a quick summary of this work. So can we reduce the dependency on trivial order? Yes, we can do that by dividing the long context into smaller pieces. Can large language models resolve the conflicts in the contextual information? Yes, we can do that. Do large language models favor short, brief context over long context? Yes. And what about predicting the loss in the middle issue? Yeah, to some degree we can predict that. There is still room for improvement. So yeah, that's pretty much that I have to talk about today. And here is a list of reference of the paper that I've talked about. Last but not least, this work cannot be done without the support of funding agency, without the collaborators, and this is the core members from our team. And that's pretty much all I had. And thank you so much.
Okay, so let's open the floor for discussion. Any questions? Yes. You can raise your hand and then I can hand over the microphone to you. Okay.
Yes, please.
Great talk. Thank you so much. So I'm wondering, you mentioned the RAG to improve the prediction accuracy. So I saw some papers using some reinforcement learning technique. So can you give some insights on if reinforcement learning can improve the prediction results?
What do you mean by the prediction? Which specific task you're talking about?
Like
question answering?
General summarization of prediction some disease. So I just feel, I saw some papers using reinforcement learning.
Yeah, sure.
Yes.
Thanks. So reinforcement learning, from what I read so far, is a technique in the phase of post-training. And the idea of introducing post-training is to make the models more usable and useful. What does this mean? So in pre-training, we all know that it's pre-trained based on some strategy, mask language models, for example. And the language model is capable of replicating some patterns. But when you actually play around with some open source models, you find that sometimes these model outputs are repetitive. It keeps repeating the same sentence again, again, again. Well, you play around with GPT. It doesn't have this sort of problem. And what's the difference? They adopted a reinforcement learning technology, reinforcement from human feedback. And that's how they improve the usefulness of the language model. Well, reinforcement learning, I talked to some friends from industry. I wonder what is the magic in reinforcement learning, and they tell me they still require a large amount of data collection. Well, we can read some news. Recently, Meta acquired a startup company called Scale AI, and the major business of Scale AI is to data annotation for those large giant tech companies, for example, Google. So that's my idea about reinforcement learning. Well, yeah, I think reinforcement learning in general, it also applies to some planning as well. So nowadays, agentic AI becomes a real thing where the AI can come up with a plan to approach some complicated task. They break the task into smaller pieces of subtask milestones, and I think that's where reinforcement learning can also play a role. Yeah. Thank you for the question.
Thank you. Any other question?
Hey, great talk. Thank you. My question is, is there any sort of explanation for why the short context is preferred over the long context? And was the long context just like an additional blurb of words, or was it more useful information?
Thank you. So the question is why in my system, the language models favor short context over long context. So Great question. So short context, let me elaborate this again. So in this controlled experiment, I guarantee that the documents contain the key information is included in the context. So by reducing the length of the external knowledge source, I increase the density of the key information. If you think about Oracle setting, it contains nothing else, just the key information. So it's not going to be, it doesn't require the language model to distill the information from a very long external knowledge, which contains a lot of irrelevant documents. But rather, just go to the documents, go to the key information directly and pick that up. So imagine in the Oracle setting, there is no noise in the retrieval results. It's just a matter of information extraction. It doesn't even require any understanding of context or the question. And when in the long context, the key information is mixed with many irrelevant information. I wouldn't call them noise. Sometimes even include some contradicting information. And that's why it's a more challenging task. Does this answer the question? Thank you. Great.
Hi, I have a question related to last in the middle, which you talked about related to the RAG, retrieval results. So the question is, you said like in the retrieval results, we may not get all the results every time. That's why we lost some useful information. But actually when we retrieve the more results using RAG something, then we do use the LLMs to act over the retrieved results. Then we get the correct information related to the question, right? So how, if you use like LLMs to find out the key point based on the question in the retrieval?
Excuse me, let me try to understand the question.
Okay.
The question is that there are some previous work focusing on fine-tuning large language models to pinpoint where the key information is, fine-tuning that model. And the question is how language models can be fine-tuned to find those key information. Is this, do I understand the
No,
question
that's
correctly?
not my question. So we can fine-tune the large language models to find the key information. That is a laborious task because it involves a lot of annotation. So currently we use like the RAG technique to pull out the retrieved results, and then they are subjected to the LLMs. The results of RAG will be used by the LLMs to get the information based on the question. So the retrieval results, suppose I ask a question regarding one particular event that happened in like a length of 2 pages or a book is given to it, and I ask only about one particular question related to one of those pages. And what the retrieval result should do is, it should give me the similar content related to my question.
Professor Guo, could you please help me paraphrase the question? I didn't catch.
So your question is that, when they fine-tune the large language model, they shouldn't use the downstream, the file testing example? Okay.
So my question is, we can retrieve more number of results, and then we can pass those results to the LLM to get the accurate information. That is how the RAG works right now.
Yeah.
So the alternative he proposed is like to use LLMs, directly fine-tune the LLMs to find the key information.
Yes.
So how is going to benefit better than the one that is existing right now?
Oh, so
Yes.
I think his question is that currently, when you use the RAG, you assume that you can get the accurate information, right? And so that's, but in your case, you are using the file tuning, right, to also trying to adapt it to the downstream task. So what's the comparison between those two approaches, right? That's the question. Your file tuning versus, you just use the RAG,
It sounds like the question is based on an assumption that nowadays the retrieval systems can perform very well. We already can pinpoint this key information. So that being said, we will include no noise in the retrieval results. But I want to bring this up. That is not true in the medical domain. So we are working on some papers. I want to share some findings. For example, when user input a query, because of the natural language in nature, retrieval task in biomedical literature is no easy task. Years ago, there is this condition called heart failure or kidney failure. They are not called failure anymore. They are called heart disease or cardiovascular disease. really depending on what retrieval system you are using. If you are using inverted index, you will see that if the condition or interventions are described using different names, using alias, inverted index simply cannot retrieve the full result, all the latest findings or previous existing knowledge. But if you are using MIT-CP dense retrieval, where the queries and the documents are embedded in as an embedding vector, that's a different story. Well, seemingly the benchmark performance show that the dense retrieval are also very compatible, but they have the black box nature. If there's something goes wrong, there is no fix. We do not know what goes wrong. And I want to ensure that in real practice, most of the retrieval system, they are not built on top of large language model in the spirit of cost effectiveness. What they use to encode the query and documents are based on small model checkpoints like BERT. And the BERT encodes, when the BERT encodes the query and documents, semantic similarity does not guarantee semantic equivalence, semantic relatedness. So it's just a semantic. I have an example. So I input a query that describes a benign tumor, and then the results give me a malignant tumor. This is because the embedding vectors, they capture and return some closely related concepts, but there is no guarantee on equivalence of the semantic. So I would say in general domain, why? So the next question is going to be why the RAG seems to work so well in general domain, but not work that well in biomedical literature. That's because the amount of efforts that have been devoted. At the beginning of developing large language models, there is really a lot of efforts caring about the medical community. And all the data are crawled from all over the internet, from Wikipedia, from the big crawler. And some are from the Wikipedia, they are really not in-depth knowledge. They are what's the content? Everybody can edit Wikipedia knowledge. But for those domain that requires in-depth knowledge, I would say large language model is not that powerful, and there's still large room for improvements. And that's why before we adopt this technology, we want to benchmark, we want to know how safe, how much trust we can put in this language model input. So long answer short, retrieval system in medical domain is still challenging. I'm just talking about literature. I'm not even mentioning clinical notes. When doctors writing discharge summaries, they are very busy. They don't have the time to write everything very cohesively and consistently. So there are some challenging nature in this specific application scenario. Thank you for the question.
Thank you very much for your speech. And I have a questions regarding that you mentioned about that there's still the need to involve like the human experts for the evaluations of the large language model prediction results. And of course, this is the general problem that's faced by the generative AI in the medical fields. Like the clinicians or the experts cares more about whether the prediction is accurate or not, rather than whether the contextual thing is similar or not. Therefore, I'm wondering whether your teams have thought about like any perhaps potential matrices that would help like the human besides the human experts to help to predict the accuracy of the generated results compared to the original one. Not only contextual similarity, but also the accuracy of the results compared to the original ones.
Sure. Thank you. So the question is about, we mentioned some challenges in evaluating, specifically for text summarization, right? The measure, we mentioned that some measures only measure the overlapping between the reference summary and the machine-generated summary. Why don't we design some more sophisticated measures that can more accurately depict the quality of the machine-generated content, right? This is a very good question. I think this is a long story. This is a legacy from machine translation. In the world of machine translation, because back then people were still relying on n-gram models to predict a sequence, and even generating a readable sentence is a challenge. So back then, overlapping is a very good indicator of readability. Now we are not even talking about correctness or semantics, just readability. So this Rouge score or blue score, they have been adopted for several decades, and people still keep using that. It's just that all of a sudden we found that the quality of machine-generated content has been significantly boosted, and we figure out we need a better quality measurement to address this task. But has there been any efforts devoted on this? Definitely, yes. So when BERT was invented, people have already thought about something called BERT score, whether we can let the BERT model to perform a regression task given a pair of sentences and see how well they align with each other. Yeah, that's one direction. And the BERT score is indeed a fully explored area. And the problem, BERT is neural networks, is black box. We have no clue why this BERT model determines this pair of sentences deserve a better score than the other pair. That's one thing. And then another challenge is that we still could not figure out a way that so concretely describe the quality. This is an open-ended question. So I'll give you an example. So for example, if you paraphrase this sentence, let's just forget about summarization. Let's just think about sentence paraphrase. One sentence is saying, this room is cold. And the other sentence is chill out there. The semantics are very similar, but they lack an overlap of keywords, semantically meaningful keywords. But on the other hand, if you say a word, just a consecutive sequence of four words, cold, 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 you'll find that automatic evaluation metrics are measured. Because they have an overlap, they cheated the system. This is like the phenomenon you described. But I know there are some ongoing efforts. I know there is a group in University of Texas at Austin. They are trying to build benchmark and models, how we can verify that all the sentences, all the contents generated by the language models can be verified against some high-quality resources. So I guess that's going to be one direction to verify the correctness of machine-generated content. But this is open-ended question. It's not like people do not care. People do care, but we don't have a solution yet. Thank you.
Okay, so any other questions? Okay, so maybe I can ask the final question, okay? So basically, large language models have been used in many domains, right? Not just health or their energy, finance, or everything, right? So my question is that, when we apply or, using the large language models to address medical problems, so what are the unique challenges that we should consider compared with other domains? For example, you talk about the retrieval augmented generation, right?
Yes. Yes.
And while this retrieval augmented generation technique can be used in other domains as well, right? So when you apply this to the medical domain, so is there any unique aspects or challenges that you need to consider?
You mean in medical domain or?
Versus other domains, and for example, they are kind of just like the chat box, those kind of other general domains, right? Not just the medical domains. So is there anything that we need to pay special attention to?
Yeah, sure. Thanks for the question, Professor Guo. Yeah, in general, deploying large language models have many we need to take care of a lot of things. It's very computation intensive. So in order to prepare a model, we need to pay some cost on the hardware for pre-training. That's applicable to most of the domains, regardless what you are working on. Yeah. But there are some factors, they indeed vary domain by domain. For example, there is one domain that I cannot envision any difficulty. That is entertainment. So if you ask language model or any diffusion model to generate content just for entertainment purpose, there's nothing wrong. As long as you abide the policy, right? As long as it's entertainable, it's fine. So I would not expect any challenges in deploying AI models in those domains. But in medical domains, in my opinion, I think, for example, I'm working on medical informatics. This is a relatively premature field as compared to some well-established like EE, like computer science. I think one of the challenge is that there is a lack of standardized evaluation. Recent years, those top-tier conferences are receiving tremendous increasing amount of benchmark work. People are proposing how we should benchmark documents. One of our collaborators, he's the author of PubMed QA. That's a benchmark that has been widely used and is well known, is well reputed. But there's limitation. If you think about some of the benchmarks, how they're constructed, back then there is a lack of standard benchmark. As long as something that can tell you something about the performance, people are happy with that. But later on, when people realize that this benchmark is not good enough, we still need a better indicator for the system performance. That's going to be one of the challenge. And the other, so I would say at this point, annotating data is still the most time-consuming part. It's the most tremendous part that requires the most efforts. After we are having a very high-quality annotated data set, we can start from there. Whether we want to scale out the data annotation, or whether we want to automate the data annotation, or if we want to prepare the model with better capability on top of this data, we can talk from there. But right now, the biggest problem that I can think of is from the data, high-quality annotated data.
True, yeah. Actually, for the benchmark issues that you mentioned, so we all know that it's very complicated. So that's why, OpenAI recently, released their benchmark, right?
Oh, yeah.
Perhaps is one of the, major initiatives that they are trying to address that issue.
Right.
That's true. Okay.
Yeah, it's glad to see that the community is paying more and more attention to medical fields. OpenAI just released a benchmark for medical fields. Yes, like you said.
Yeah. Okay. Let's thank the